As I've said in many of my videos, none of this is my field. I just do this for fun. In particular, on this video, I wanted to explore the drag equation and see what I could learn. I don't know anything about engineering, but I haven't seen any experts make videos explaining this. And if they did, I doubt it would be on a high school level, so that's what this video is. I wanted to get the drag coefficient of one of my arrows. I have about a 50-pound recurve bow, so not terribly heavy on the poundage, and it's a recurve, so fairly slow arrows compared to a compound. So I wanted to see if I could get that coefficient of drag. And actually, I'm not even interested in the actual number of the coefficient of drag. I'm never going to use that. I'm actually just curious to see if I could obtain the coefficient of drag. So that's what this video is. This is an exercise in procedure and not in exact numbers, meaning I wasn't worried about getting the cross-sectional area of my arrow perfect, and I don't have any way to measure the cross-sectional area of each feather on the arrow. And I have a chronograph that measures velocity of the arrows, but I don't know how accurate that is. So at any rate, like I said, this is just an exercise in procedure and not exact numbers, to see if I could at least get a ballpark of a drag coefficient that made sense. So drag equation, 1/2 rho v squared cross-sectional area times coefficient of drag. Rho is your air density, 1.225 kilograms per cubic meter on some reports from Google. Velocity, meters per second. Area is cross-sectional area. Remember to keep everything in meters. That's the tricky part. I'll go ahead and write that here. And then that's the drag coefficient right there. Just to thoroughly play with the drag coefficient here. Other people have toys. I have equations I play with. I wanted to see what the units would be on the drag coefficient. It's reportedly no units, so let's see if that's true. We got our force will be in newtons, air density, velocity, cross-sectional area. Change all of these to the appropriate units. Newtons is actually kilograms, mass times acceleration, which will be kilograms times meters per second squared. Bring all this stuff underneath. So this right here will be the numerator, all this will be the denominator. Now that we brought it underneath, bring it back up, but invert all of our fractions, because when you divide by a fraction, you invert it. So bring up all your fractions, go through and see if everything cancels. So kilograms canceled, seconds squared canceled. This one right here is a little tricky because we got meters to the third times meters, meters squared. So let's just add up all of our exponents. 2 and 2 is 4, 3 and 1 is 4. So meters will cancel as well. We're left with 2 and no units. Here's the stats on my arrow. 8mm diameter. Don't forget to change that to radius when you're figuring cross-sectional area. The way I got this, I don't have any fancy calipers or anything. I just stuck the arrow between two boards and then measured the distance across both boards. At 0 meters, I got 185 feet per second, 15 meters, 180 feet per second. I converted those to meters per second. Mass of the arrow is 374 grains. That's 24 grams. I have a conversion app on my phone that converts all of these numbers for me. I used a chronograph for these measurements. The velocity varied by about 3 to 5 feet per second. So I just took a rough average, and I wasn't even super careful about getting that average. Like I said, this is more of an exercise in procedure instead of exact numbers. The distance I shot was point blank versus 15 meters, so I could see how much the arrow slowed in that distance. That's an important number right there because I use that later in an equation to get acceleration. I would have went back farther, but that was all the distance I had to shoot through the chronograph. Let's set up our drag equation right here. Isolate our coefficient of drag right there. We can't just start plugging in numbers willy-nilly just yet because we have to derive some of these numbers. First off, I'm going to get an average velocity of 55.5. That's halfway between 55 and 56. Now, everything I read said that you really can't use an average velocity to get your coefficient of drag. but I reason that I can use somewhat of the squeeze theorem taught in calculus, where I simply squeeze two numbers together until they're almost the same number. So for example, I just take this distance right here between 0 and 15 meters. If I'm given a really big spread, say between 30 and 60 or something, I simply close that distance and get that distance smaller and smaller until these two velocities are almost identical. I didn't actually have to put any effort into this because I just shot at 0 meters, then shot at 15 meters, and I had numbers that were almost identical. So I've got a really close range right here to give me a really good approximation of velocity. Having a pen and some scraps of notebook paper is a lot cheaper than building a wind tunnel and getting some sort of sophisticated device that can measure force on something that's held up in that wind. In addition, I got to put some brain cells into this to figure out how to squeeze those numbers together to get a reasonable approximation of velocity. Is this proper? I don't know. This isn't my field, but it seems logical. Anyway, so now that we have our starting and ending velocity right here, let's plug those into the equation. V final squared equals V initial squared plus 2AD, just a kinematic equation from introductory physics. Plug and chug. Go ahead and isolate our acceleration right there. So it'll be this minus this divided by that, and I'll get an acceleration of 3.7 meters per second squared. Plug that into this equation. Mass times acceleration equals force. We have the mass of the arrow, which is right there. Don't forget to change that to grams, or sorry, change that to kilograms, and you'll get a force in newtons, 0.09 newtons. Okay, now we have our force, our drag force. Now we have our velocity. Cross-sectional area, I've made these mistakes more than once. Don't forget to change the diameter of your projectile into a radius. And I think I mentioned I just held the arrow between two boards and measured the distance across the boards. I figured that's about as good as some fancy expensive calipers. And then once you get your radius in millimeters, don't forget to change that to meters. So that'll be 0.004 meters. And then I square that, multiply it times pi. Pi r squared is area. That's what I get right there for area. Okay, go through the math. I get 0.97 for the coefficient of drag on my arrow. And come to think of it, if I were to include the cross-sectional area of the fletching, I'm thinking that would be immeasurably small, so it really doesn't matter. Granted, those feather fletchings do slow the arrow down more, I imagine, than the plastic vanes. But at any rate, that's a reasonable number, so I had fun doing that.